Can you all hear me? Sounds like you can. You can't see me right now. That's all right. We're getting started here. Plus, at least that's working out. Okay. Let's see if we can get the other part to work. That's concerning. You guys see that message on the screen there? In 10 minutes, power will turn off and go into standby mode. There might not be anything I can do about that. Well, we'll do what we can. Why are you being so difficult? Every piece of technology I'm making me. There we go. Great if this one would work as well. It's your problem. Sneaking suspicion we might have some issues today. Success. All right, you all have to, I'll probably notice it, but if that turns off, which I'm worried it's going to turn off, let me know. I'm not sure what we're gonna do if that happens, but let's see. Yeah. So we had talked a bit about polar coordinates last time and graphing polar equations. We're going to try to talk a bit about calculus of polar coordinates. So let's do a few things with that. So yeah, I don't remember if we did this example last time or not, but let's kind of start here. So we are Co-21B. This is June 4th. Some calculus with polar coordinates. When people say calculus with whatever, polar, parametric, they really just mean like derivatives, integrals, stuff like that. Calculus with polar coordinates. And yeah, I do think we did this one last time. So I'll remind you that last time we found the slope of the curve r equal to 1 minus sine theta at theta equal to 0 radians. That was the very last example I think we did last time. It was a little bit gross because we had to kind of do it parametrically. So what we did last time was we said, well, dy dx is equal to dy d theta over dx d theta. We're thinking of this parametrically, but instead of using t as our parameter, we're using theta as our parameter. And then we're imagining, or not imagining, we're using the fact that x is equal to r cosine theta, y is equal to r sine theta, but then we can think of r and just r as a function of theta. So this is really equal to some function of theta times cosine theta and some function of theta times sine theta. Specifically, the function of theta is 1 minus sine theta. So then when we did this, we got dy dx equal to, let's see, so dy d theta was product rule f prime of theta times sine of theta plus f of theta times the derivative of sine of theta, which is cosine of theta, over, now we take the derivative of x, which is going to be f prime of theta times cosine theta plus f of theta times the derivative of cosine is negative sine of theta. And then we actually wrote it out. The derivative of this function of theta is going to be negative cosine theta. So you get negative cosine theta sine theta plus 1 minus sine theta times cosine theta over negative cosine theta again times cosine theta plus 1 minus sine theta times negative sine theta. And then if you plug in 0 for theta, you're going to get that dy dx is equal to negative 1 times 0 plus 1 times 1 over negative 1 times 1 plus 1 times 0, which is 1 over negative 1, which is negative 1. So if you have a curve defined in a polar way and you want to still find the slope of a tangent line, you still find the slope of the tangent line parametrically, but then you have to think of your parametric equations as being y and x both functions of theta, and you replace the r in the x equal to r cosine theta and the y equal to r sine theta with whatever the function of theta that r is equal to is. It's kind of a lot. And then we could ask something like, what is the length of this curve, of the cardioid? R equal to 1 minus sine theta. And when you ask for the length of a curve, usually it's a good idea to be, well, it'd be nice if they just gave us the limit of integration. It's often either going to be 0 to pi or 0 to 2 pi. This cardioid looks like this, where at theta equals 0, it's 1. theta equals pi over 2, it's 0, at pi it's 1, and then at 3 pi over 2, it's equal to 2. So it's kind of like that. Right, if you plug in, at this point here is theta is 0, r is 1. This point here is theta is pi over 2, r is 0. This point here is theta is pi, r is 1. And this point down here is theta is 3 pi over 2, and r is 2. Right, direction, length, direction, length, direction, length, direction, length. So then the length of this cardioid is going to be the integral from 0 to 2 pi of the square root of, well, it's the usual length formula, done the parametric way. Okay, usual baby just starts there. It's the typical length formula where it's the square root of either 1 plus dy dx squared or 1 plus dx dy squared, or when it's parametric, dx dt squared plus dy dt squared, or when it's parametric in terms of theta, dx d theta squared plus dy d theta squared d theta. Let's be smart and not repeat the work we just did. That's dy d theta right there. That's dx d theta right there. So interesting. I don't know how to teach this to the people on Zoom and people in the classroom without having the projector. Anyone have any bright ideas?
Use your camera to bright up, like.
Yeah, I could probably. So okay, we'll have to ask the folks on Zoom how this looks. So I'm gonna turn you up. So all right, we'll try angling the camera at the board. See how that. Oh, that's a lot of me. That's a lot of upside down. Can we get this? I might be smarter than just trying to turn this over. 1 second. Let me try and see how this looks here. So for those on Zoom, give me a moment here. We'll try to. We're going to use the board. It's going to be real fun. So let's revolve this. Let's see. Good times. Wow. I know there's a way to revolve like the camera view here. 1 second. Exposure. I thought there was a way. Oh, I think it's a button on here actually. Yeah, there we go. Wow, that's a lot of me. There we go. Okay, it's a lot. I know. There's a lot of my face in camera there. There. Okay, great. So hopefully we can zoom out. That's as far. Oh man, I don't know about this. Okay, give it a try here. It's up. Okay, let me do a couple things. Sorry for the technical difficulties today. It's beyond my control, unfortunately. So I lost the. Sorry, I have to do a couple things because I lost that screen there because I turned it off. Oh, challenging times. Okay, let me do that. No longer extend. Cool. Yeah, okay. All right. I think. Oh, wow, I think I'm giant in screen there. Hopefully, you all can see the board pretty okay. All right, let's give this a go. Did I bring pens? I did bring pens. Good. It's always good to have pens in your backpack. All right, so I'll try to stay. Let me turn this so I can see myself forward. So I try to stay out of the way of things. So we were doing this. So we were about to calculate the length of this cardioid, which again looks like this. And it's gonna be the integral from 0 to 2 pi and the square root of dx d theta squared plus dy d theta. A lot of these polar calculus things are really just parametric calculus things, but reworked to be in terms of theta instead of in terms of t. So our dx d theta, and actually this is where it'd be a good idea to simplify things. See, can we see here? No, not quite. Okay. So our dx d theta, probably should write this down again. So our x was 1 minus, sorry, bring 1 minus sin theta times cosine theta because it's your r cosine theta. Your y is 1 minus sin theta sine theta. Our dx d theta was negative cosine theta times cosine theta plus 1 minus sine theta times negative sine theta. I feel like I'm making a mistake here somehow. No, that seems all right. Oh, right. I'm okay. Yes. And our dy d theta product rule again is just going to be negative cosine theta times sine theta plus 1 minus sine theta times cosine. And I definitely think before we square these things, it's probably worth our while to simplify them. So we simplify this, we've got a negative cosine squared theta plus 1 times negative sine is a minus sine of theta. And then we have a negative sine times negative sine, so that's a plus sine squared. That's gonna be real gross. And here we've got a negative cosine sine. We've got a plus cosine. And then we've got another negative cosine sine. That's, yeah, it really is as gross as I think it is. Okay. Oh. That's interesting. I'm doing too much work. Am I really doing too much work? Sorry, I'm just looking at this and then noticing that this is, so I should be smarter about this. Let's back it up. Let's go more general. No, I just roll it out. So let's write this way. So the integral of the square root of, so dx d theta, writing it in the general way where x is f of theta cosine theta, y is f of theta sine theta. We get dx d theta, which is again still kind of gnarly, f prime of theta times cosine theta minus f of theta times sine theta, or I should say plus f of theta times negative sine theta squared plus dy d theta squared, which will be f prime of theta times sine theta plus f of theta times cosine theta squared. All right, let's do the dirty work of multiplying these out. See what we get. So when you square this out, you're going to get this quantity squared. So f prime of theta squared times cosine squared theta. And then you're going to get a minus 2 f prime of theta cosine of theta f of theta sine of theta. Wow, that's gross. And then plus this thing squared, so f of theta squared sine squared theta. And then you're going to get almost the same thing here. You're going to get f prime sine squared. So, sorry, that's a little bit messy here. And then you're going to get 2 times f prime times sine times f times cosine. On the square root over. And then finally, you're going to get f squared plus times cosine squared. Okay, here's what we want to see. So the minus 2 f prime cosine f sine cancels with the positive 2 f prime sine f cosine. Great. And the f prime squared cosine squared plus f prime squared sine squared is going to be f prime of theta squared times cosine squared plus sine squared, which is 1. That term plus that term. That's just f prime squared. And then f squared times sine squared plus f squared times cosine squared is also just f squared, because it's times f squared times cosine squared plus sine squared. So it's f of theta. I think I saw something pop up in the chat there. Yeah, sorry. Sorry if it doesn't look great. I can try to, let's see if I can move this a little bit. I think, or just ruin the video completely. Yeah, sure, just break it. Oh, is it? So the problem is, it's a bit heinous. Sorry, I've just somehow the visualizer just went away completely for me. I can't see it any longer. But the point here, I would say, is that it's gross, but it actually works out to be very nice. I know you can't see what I'm pointing at. Give me 1 second. Sorry. Yeah, I thought you meant the video quality as well. Apologies. Thanks for sticking it out with me. Again, wish it was less problematic. Gosh. And of course, my document camera seems to be acting funky as well. Okay. Yeah, great. I guess I could just do that. Let me just try instead to, I guess I don't need to use the document camera. Let me just pin my video here. That's, can you guys see that okay? I feel like now the video quality is less than excellent. So, okay, good. Let me just, let me mirror my video so things don't look backwards to me. Great. Okay, so the long and the short of it is, if you have x and y as polar equations, x equal to r cosine theta, y equal to r sine theta, and we're imagining f of theta is our r, and r is a function of theta. In this case, r equal to 1 minus 1 plus sine. Then it boils down to just having this here, the square root of f prime of theta squared plus f of theta squared. Or if you want to write it, or r is your function of theta, you can think of this as the integral of the square root of dr d theta squared plus r as a function of theta squared. So, not the best thing I've ever seen in my life, but not incredibly heinous. So in this problem, we want to find the arc length. We can say that our arc length is going to be the integral from 0 to 2 pi of the square root of, remembering that r is 1 plus sine theta, dr d theta squared, so that's going to be cosine theta squared, plus r squared. Which is not that bad. If we multiply out the inside of the square root, we get the integral from 0 to 2 pi of the square root of cosine squared theta plus 1 minus 2 sine theta sine squared theta. Then that ends up equaling the integral from 0 to 2 pi of the square root of cosine squared plus sine squared is 1, 1 plus 1 is 2, so we have 2 minus 2 sine theta. And there's a couple ways to do this problem. The way I usually think about doing this is trying to rewrite it as a trig identity. Ooh, trig identity? Is that what I'm really thinking here? No, I guess not. I mean, yes, but not the one I was thinking of. So what I'm going to do here is I'm going to factor out the 2 inside. I have a 2 times a 1 minus sine theta. I'm going to multiply the 1 minus sine theta by its conjugate. So 1 minus sine theta over 1 and multiply by 1 plus sine theta over 1 plus sine theta. That's a fairly common trick to use if you're dealing with something trigonometric and you don't know what else to do. You see a 1 minus sine or a 1 minus cosine or 1 plus sine or 1 plus cosine to multiply by its conjugate to make something kind of pop up. So then here's what we've got. We've got the integral from 0 to 2 pi of the square root of 2 times 1 minus sine times 1 plus sine is 1 minus sine squared over 1 plus sine. Do I have an eraser? Yes, I do. And then, yeah, this is a brutal problem. 1 minus sine squared, excuse me, is cosine squared. And 1 plus sine is still what it is. Yeah, this is an awful problem. I'm not a fan. So then you can break this up as the square root of 2 integral from 0 to 2 pi. The square root of cosine squared is cosine. The bottom is the square root of 1 plus sine. And then you can do a u sub. U equals 1 plus sine theta. Du is equal to cosine theta d theta. We might as well change our limits of integration. If theta equals 0, u is going to equal 1 plus sine of 0. If theta equals 2 pi, that's interesting. That seems problematic. U is going to equal 1 plus sine of 2 pi, which is also 1. And I'm going to be integrating from 1 to 1. There's an issue here. Yeah, oh, interesting. Yeah, I know what the issue is. So you know how most of the time we take the square root of cosine squared and we're like, yeah, it's fine, it's just cosine. Well, here it's 5%. So changing this is kind of a problem. I would probably just, this problem's little. Yeah. Interesting. Okay. So what so smart person did, instead of going from 0 to 2 pi, is they said, well, it's the right half of this cardioid, or it's all of this cardioid. And this right half is actually half, and that goes from theta equals negative pi over 2 to theta equals pi over 2. So then what we're going to do is we're just going to double that. So instead of doing this, smartly say, it's double the integral from negative pi over 2 to pi over 2. Because from negative pi over 2 to pi over 2, cosine is always positive. So the square root of cosine squared isn't the problem. You don't need the absolute value. And then we can still do the same u sub, but now our limit of integration, if theta is negative pi over 2, sine of negative pi over 2 is negative 1, 1 plus 1 is 0, and theta is pi over 2, 1 plus sine of pi over 2 is 1 plus 1, which is 2. So then we are going to get 2 root 2 integral from negative 1 to 1 sorry, not the other one, 0 to 2, apologies. And then we have our cosine theta d theta, which is our du over the square root of 1 plus sine theta, which is the square root of u. And we're almost done, finally. This is 2 root 2. We're integrating u to the negative 1/2. We're getting u to the positive 1/2 divided by 1/2, which is times another 2. From 0 to 2. And finally, we get 2 root 2 times 2 times 2 to the 1/2 minus 0 to the 1/2, which is 2 times 2 times the square root of 2 to the square root of 2, which is another 2, which is 8. Good God. So kind of interestingly, this very, curvy shape has a length of exactly 8. Which I think is, I think that's maybe surprising. You might imagine there would be like a multiple of pi or something, but no, it's literally 8 units long. It's kind of cool. Wow. So hopefully you're not going to see any of these, to be perfectly honest. Or at least ones that are, this one's kind of pretty basic, right? Like this is a fairly straightforward polar equation, and its arc length is really awful. They probably get worse. There might be a slightly easier one if it was like just a straight circle. In fact, if it was a circle, you would know what the arc length was because we know how to find the circumference of the circle. So I don't think we should do this necessarily, but I would point out that over here. I have not erased the board in like forever. It's just using a new piece of paper. So I should say that if someone gave us, say, the polar equation r equal to 6 cosine theta, which is a circle, and the way I would graph this is by finding one of the two of the endpoints actually. I would plot theta equal to 0 radians, sorry, these aren't degrees, and theta equal to pi over 2 radians. So if theta equals 0, I'm pointing to the right. Cosine of 0 is 1, 6 times 1 is 6. So I get this point here where theta equals 0, r equals 6. And then if theta equals pi over 2, cosine of pi over 2 is 0, which means you're at the origin if your radius is 0. So we just get that point there when your theta is pi over 2 and your radius is 0. And these two angle values for a circle like this will always give you the endpoints of a diameter. So my circle is this circle. The center is halfway between 0 and 6, which is 3, 0. So the radius of the circle is 3. And we know that the circumference of the circle, or the arc length of the circle, should be circumference, which is 2 pi times the radius, which is 6 pi. So one should be able to show that the arc length is the integral, we'll talk about the limits of integration in a second here, of the square root of dr d theta squared plus r squared. Well, this one's going to be not terrible. Should have started with this. Sorry. Sorry I didn't start with this one for all of us. Dr d theta is 6 times negative sine theta. Squared. And r is 6 cosine theta squared. And we're going to end up with the integral of the square root of 36 sine squared plus 36 cosine squared. That's just 36, and the square root of 36 is just 6. This is really just the integral of 6. Now, the question is, for this entire circle, what should my limits of integration be? So I know I only talked about this briefly last time, but for a circle like this, and I know we actually drew it out, right? From here to there, that was theta equals 0 to theta equals pi over 2. And then from here to there, it's the other half where you go from theta equals pi/2 to theta equals pi. So the full arc length of this shape, the full circumference of the circle, is gotten by integrating from 0 to pi. Then we integrate and we get 6 theta, 0 to pi, which is just going to be 6 pi minus 0. So at least it's kind of neat to the shape that we actually know the arc length of. The formula does show us that we actually get the arc length that we think we should get. Okay. Let's take a look at one of the other calculus things using polar. So certainly I should point out though that if you're doing polar, sorry for those of you that don't hear as well, if you're doing polar, this is the equation that you actually want to use for arc length. You don't want to like do the long thing I was trying to start with because I forgot there was this easier equation. It's just the integral of the square root of dr d theta squared plus r squared, which is not nearly as bad as what we were trying to do for a second. And yes, in case you hadn't realized, right, I'm not gonna be able to post any notes for this class today because, right, it's on the board. So you're welcome to take a picture if you want. Certainly the video will get posted later, but it might be hard to see with it. So do what you will with that. I guess I should call like IT or whatever and get this bulb situation dealt with because I might be able to actually use it last very long today. Okay, so the other thing we have is the area. The area of specifically the cardioid. In cardioid we're doing for. I think it actually was 1 minus sine theta. Sorry if I wrote 1 plus sine theta before. The cardioid we were doing was 1 minus sine theta. Yeah, right? Yeah, it was. Yeah, I apologize. So I think somewhere in the past, so probably erased by now, I might have actually written an article to 1 plus sine theta, but it is in fact article 1 plus. This is your reminder, right? Because when theta equals 0, you get 1 minus 0. When theta is pi over 2, you get 1 minus 1. When theta is pi, you get 1 minus 0. When theta is 3 pi over 2, you get 1 minus negative 1, which gives you 2. So now we'd like to find the area of this cardioid. So the idea for the formula here, and it's actually not too terrible, is that if you have just some sort of circular shape, we know that the area of I like to call it just a slice of pie, but it's the area of a sector of that circle. So the area of this sector, if this length is some radius, the area of that sector, or slice of pie, is 1/2 times your angle times your radius squared. It's not a formula that I'm particularly using a lot, but what I like to think of is, you go all the way around the circle, what's the angle all the way around the circle? 2 pi, and the area all the way around the circle is 1/2 times 2 pi times r squared, which is exactly pi r squared. So it seems like this is a reasonable formula for the area of a slice of pie. So we're going to use that to inform us as to how to find the area of any shape. So basically the idea is you're taking some like little angles worth of theta and you're saying, well, if you make this angle small enough, let's call it a d theta. Wow, sorry for the terrible writing. If you make that angle small enough, then these two lengths are essentially the same. And so that the length of this, the length of this little segment here that has an angle of d theta, that area is going to be 1/2 r squared times d theta. And then to find the total area of the cardioid, we're going to quote unquote add up all the areas by integrating. So total area is going to be the integral from 0 to 2 pi. I might need to do a, yeah, we can do it, 0 to 2 pi. Of 1/2 our r as a function of theta squared d theta. That's the gist. So then, same sort of thing we've been doing. That's going to be the integral from 0 to 2 pi. Pull the 1/2 out front. 1 minus sine of theta quantity squared theta. Multiply it out. We get 1/2 times the integral from 0 to 2 pi of 1 minus 2 sine theta plus sine squared theta d theta. And the sine squared theta is always kind of a pain. We replace, whenever you have sine or cosine to an even power, you have to use that trig identity. So this is going to be 1/2 the integral from 0 to 2 pi of 1 minus 2 sine theta. And then sine squared theta is equal to 1/2 times 1 minus cosine of 2 times theta. And now we can integrate this. So that's going to be 1/2 times the integral of 1 is theta. The integral of 2 sine theta is negative 2 cosine theta, so that's going to be a positive 2 cosine theta. The integral of 1/2 times 1 is 1/2 times theta. And the integral of 1/2 times negative cosine 2 theta is going to be negative 1/2 times sine 2 theta over 2. From 0 to 2 pi. Good news, when you take sine of 2 pi or sine of 0 or a multiple of 2 pi or a multiple of pi, it comes to be 0, so a lot of these just go away. So you end up getting 1/2 times 2 pi plus 2 times cosine of 2 pi is 2 times 1 plus 1/2 times 2 pi is pi. And then sine of 4 pi is 0. Minus, when we plug in 0, we get 0 plus 2 times cosine of 0 is 2. Plus 1/2 times 0 is 0. Plus sine of 0 is 0. So we end up getting the 2 here and the 2 canceling. We get 1/2 times 3 pi, which is 3 pi. That's the area in this entire cardioid. Seems fine. Okay, so. Sure, let's do one more area. Because I feel like this one is kind of worthwhile. Okay, so after this, I'm happy to do other things. They do not have to be polar things. We can go back to other topics if you guys want to. Let's say we want to find the area between, or the area common to the intersection or sorry, the interior is not the intersection, apologies. Words. Come to the interiors of r equal to 1 minus sine theta, the cardioid we've just been looking at this whole class, and r equal to sine theta. So let's draw them. So once again, here's the cardioid we've drawn a few times. It has value 1 here, 0, 1, like that. And then r equal to sine theta. Well, once again, whenever you have r equal to a multiple of sine or a multiple of just cosine, it's a circle. The circle centered on the appropriate axis. So if it's cosine, it's the x-axis. If it's sine, it's the y-axis. And I'm just going to graph it by finding the endpoints of the diameter. So for this one here, if I set theta equal to 0, I get r equal to 0. Not particularly helpful. I set theta equal to pi over 2, I get r equal to sine pi over 2, which is 1. So that's the point up here. So this point and this point are the endpoints of the diameter of my circle. So here's my circle. So what I'm trying to find is the area that is inside both of these curves. So this region here and this region here. And it seems like I could probably use some symmetry properties to double just one of these areas. So let's look at this right-hand one specifically. Let's kind of blow it up a little bit. So I've got that part of the circle, this part of the curve. This equation, r equal to sine theta. This equation is r equal to 1 minus sine theta. So I need to kind of figure out for what values of theta these two things intersect so I can find my limits of integration. So when you're trying to figure out what's going on here, we're essentially kind of imagining radial lines shooting out from the origin. So for this kind of first half of this, my radial lines are shooting outward and they're hitting the black curve, r equal to sine theta. And then I'm going to reach some angle here, which I haven't found yet. It's going to be theta equal to something. And then after that, the blue function, r equal to 1 minus sine theta, is going to be my boundary. And apologies if you can't see this very well on the Zoom. So, right, from theta equals 0 to theta equals some angle, we're going to have r equals sine theta as the area we're finding, or the curve we're using as our boundary for the area. And from theta equals whatever to the next value is, then we're going to use the other function, the r equals 1 minus sine theta. So we're essentially breaking this up into two integrals. It's this area plus plus that area. These are different functions. So let's find where they intersect. So if we set 1 minus sine theta equal to sine theta, that's going to be 1 equal to 2 sine theta. It's going to be sine theta equal to 1/2. And sine theta equals 1/2 when theta is equal to pi over 6. So this angle right here where these two things meet and we change from one to the other is pi over 6. So for this bottom part, we're going to do the integral from theta equals 0 to theta equals pi over 6. Because when our angle is 0, yeah, right, yeah. So when our angle is 0, you're getting this one being 0, the black one. And so that's going to be, we're finding the area again, so it's going to be 1/2 sine theta squared d theta plus, then the other half here for this one, it's going to be the integral from pi over 6 to when this function hits the origin, which is when theta equals pi over 2, right? Because that's where the blue function touches down, is where when theta is pi over 2, 1 minus sine of pi over 2 is 1 minus 1, which is 0. So the integral from pi over 6 to pi over 2 of 1/2 times 1 minus sine theta squared theta. Yeah, which is fun. So same identity as before. In fact, let's be smart. Oh, it almost worked perfectly. It's really open here. So we already did the integral of 1 minus sine squared, or 1 minus sine theta quantity squared. It ended up being this gnarly thing here. Let's not repeat ourselves. Let's just use the work we've done. So integrating this, well, that we do have to say that's sine theta squared, which is 1 minus cosine 2 theta divided by 2. So this is going to be 1/2 times 1/2, so 1/4 the integral from 0 to pi over 6 of cosine 2 theta. I'm making a mistake, it's okay. I said it was 1 minus cosine 2 theta divided by 2, and then also times 1/2. So there's 2 2's we're dividing by. And then this here, we just said was all of that, so kind of terrible. It's 1/2 times the integral is theta plus 2 cosine theta plus 1/2 theta minus sine 2 theta over 4 from pi over 6 to pi over 2. Which looks really, really terrible. So we can do it though. This part here, it's going to be 1/4 times integrating this, we're going to get theta minus sine of 2 theta over 2. Evaluated from 0 to pi over 6. Plus 1/2 times, here we're going to do the evaluation, we're going to plug in pi over 2. I'm going to simplify as I go. Plugging in pi over 2, I get pi over 2. Cosine of pi over 2 is 0, so let's not write that down. 1/2 times pi over 2 is pi over 4. And sine of 2 times pi over 2 is sine of pi, which is also 0. Minus, now we plug in pi over 6. Get pi over 6. Cosine of pi over 6 is root 3 over 2. I get 2 times root 3 over 2, which is root 3. I get 1/2 times pi over 6, which is pi over 12. And then sine of 2 times pi over 6 is sine of pi over 3, which is also root 3 over 2. So you get minus root 3 over 8. So finishing this up, sometimes these problems really are terrible, as you can see. I'm gonna give myself enough room to write it right there. Yeah. So finishing these up, we've got 1/4 times plugging in the pi over 6. Pi over 6 minus sine of pi over 3, which is root 3 over 2. 2 minus plug in 0, you get 0 minus sine of 0, which is 0. Plus all that terribleness. Yeah, that's real terrible. Plus 1/2 times pi over 2 plus pi over 4 is 3 pi over 4. Minus pi over 6 plus pi over 12 is 2 pi over 12, 3 pi over 12, pi over 4. Plus root 3 minus root 3 over 8. You can probably simplify this, but I think we've done enough. Let's see what my notes say here. Yeah, it's pretty gross. Let's just leave it like that. Okay. So clearly some of these problems are really, really terrible. The takeaway here should be, if you're trying to find the area between two polar curves. Oh, you know what I forgot to do? Forgot to double it. Right, we found the area between this part, but it's there and there. So technically, our answer should be double all this. So the takeaway I would say is that trying to find the area between two polar curves, finding the point of intersection or the angle of intersection is important, so that you kind of know which piece you need to use when and where. We used the r equals sine theta piece from theta equals 0 to theta equals pi over 6. Sorry, and then we use the 1 minus sine theta piece from theta equals pi over 6 to theta equals pi over 2. And that can be kind of, I think, the challenging part about this session. Okay, so. What time is it? It is 4:05. We still have some time, so let me ask you all, and you all on Zoom as well. Is there anything you'd like me to address in the next 20 or so minutes? Any topics that are really like, you have a burning desire to see something about? It's okay if you don't. I can certainly go on, but. Sure. Surface area. Sure, but like which way? Like in terms of X, in terms of Y, or parametrically? Okay, cool. So. Yes, we can make something up that's not terrible. Stuff here. So let's speak generally for a second, and then I'll give you an example. So let's say we want to find the surface area of y equal to some function of x revolved around the x-axis from or for x between a and b. Here's the general picture. I feel like I'm sorry, I must have moved things around here. Sorry about that. Okay. So you've got some kind of like piece of this curve, and you're just revolving it around the x-axis. So it's going to kind of look like this sort of deal. What I'm really thinking about when I'm doing a surface area problem is I'm imagining some small little strip which has a length of ds. Right? It's not just a change in x, it's not just a change in y, it's kind of a diagonal change or a curvy change. And you're finding the area of the rubber band that is kind of wrapped around this surface. And the surface area of just that rubber band is the circumference of the band, which is 2 pi times whatever the radius is, times the length of the band, which is ds. And the radius is just how far away we are from the axis of rotation. So there's actually 2 ways to do this for both axes. In this case, if we're doing things in terms of, well, since I've written that function in terms of x, we're going to say this is going to be 2 pi times, I'm not going to use y there, even though I'm y away from the axis of rotation, I'm going to use f of x times ds, which is the square root of 1 plus the derivative squared. And then your total surface area would just be the integral. That would be the integral from x equals a to x equals b of 2 pi times f of x times the square root of 1 plus f of x squared. And just to kind of show, so typically you have options. Let's say that we were able to solve for x as a function of y. Meaning we could say we know that x is equal to f inverse of y, but let's just call that g of y. So this function, instead of being, or in addition to being y equals f of x, is also x equals f of y. It's kind of like we would say maybe y equals x to the third, or f of x equals x to the third. Sorry, you can say that. Okay. And then if we solve for x, we get x equal to the cube root of y, but then we would just say g of y equals the cube root of y. That kind of deal. And let's say the y limits would just be some c. So if we did it this way, the surface area of our band is still 2 pi rds. That's always what I'm thinking of when I'm doing surface area. 2 pi r ds. And when I'm doing length, it's just ds. And then we're going to integrate it. So here, my 2 pi r, well now my radius is just how high I am, which is just y. And my ds is the square root of 1 plus g prime of y squared. Sometimes in the textbook, for whatever reason, instead of writing g prime of y here, they just choose to write dx dy instead of g prime of y, but either way is totally fine. And then your actual surface area total would be the integral from y equals c to y equals d of 2 pi y square root of 1 plus g prime of y squared. Anyway. And I'm not going to write it down, but I'll say that if we were going around the y-axis instead of the x-axis, the radius would change, right? The radius instead of being f of x would just be x, or the radius instead of being y would be g of y. It's how far you are from the y-axis, which is your horizontal x distance. Okay, so let's do an actual example. Let's say that our function, sure, let's do y. Let's say that g of y is equal to y to the 5th over 10. Sorry, I have to actually put per minute to make sure the numbers come out nicely. Let's see. I'm gonna have a minus. Sorry. I want a y to the negative 3rd over 6 plus. Is that gonna work out all right? I think it is. Okay, so I want to find the surface area of this g of y revolved around the y-axis for y between 1 and 2. All right, so usual setup. Surface area is going to be the integral of 2 pi r ds. Since I'm going around the y-axis, my radius is x, the horizontal distance, but x is not a thing I'm using, so my x is equal to g of y. So in this case, it's going to be the integral from 1 to 2, bring the 2 pi out in front. My radius is g of y, and my ds is the square root of 1 plus g prime of y squared. Okay, this is where I would choose to not write everything in the integral, but I would kind of do this calculation off to the side to not kind of write the integral of the square root a bunch of times. So let's go ahead and find g prime of y and square it over here. And this is where I might end up changing it a little bit if I accidentally didn't write it as, if I don't get what I'm hoping for. But what should happen is the following. So g prime of y is going to be 5y to the 4th over 10 minus 3y to the negative 4th over 6, which we should definitely simplify. That's 1/2 y to the 4th minus 1/2 y to the negative 4th. Yeah, that should work out fine. And then we square it. g prime of y squared is going to be, if you want, you can factor out the 1/2, I suppose. I can't, I'm trying to move this board. This one doesn't move. If we square this out, it's going to be the first term squared. So 1/4 times y to the 16th, y to the 16th, not y to the 16th. I'm better than that. Y to the 4th times y to the 4th is y to the 8th. And then you're gonna have this times this, which is minus 1/4 times y to the fourth times y to the negative fourth, which is y to the 0th. But then you're gonna have it again. Right, you get it 2 times plus 1/4 times y to the negative 8th. Yes, things are looking good. Because then if you take 1 plus that, look what you get. It's gonna be 2 pi integral from 1 to 2 of g of y, which is y to the 5th over 10 plus y to the negative 3rd over 6 times the square root of, if we add 1 to that, it's going to be 1/4 y to the 8th, 1/2 plus negative 1/4 minus 1/4 is 1/2, sorry, 1 plus negative 1/4 plus negative 1/4 is 1 minus 1/2, which is positive 1/2. And then you still have the rest, which is the 1/4 y to the negative 8th. What I really want to point out is, hopefully you all can see this, yeah, is that this here is 1/4 y to the 8th minus 1/2 plus 1/4 y to the negative 8th. And factored as 1/2 y to the 4th minus 1/2 negative 1/2 minus 1/2 y to the negative 4th quantity squared. So this part here is going to factor as 1/2 y to the 4th plus 1/2 y to the negative 4th quantity squared. That is the usual pattern thing that happens with these arc length and surface area problems, if they've been set up nicely. Is that the inside, the 1 plus g prime or f prime squared, you end up getting your your g prime squared, and then when you add 1, it just changes the negative 1/2 to a positive 1/2, and then it factors back out nicely, almost exactly the same way we factored it in. So this ends up equaling 2 pi integral from 1 to 2 of y to the 5th over 10 plus y to the negative 3rd over 6 times the square root of this thing squared is just this thing. So 1/2 y to the 4th plus 1/2 y to the negative 4th. And the rest of it's, I mean, not fun, but the rest of it's relatively straightforward. Right? The rest of it is you multiply it out, you've got powers of y, and then you integrate. So we multiply that out, you get 2 pi integral from 1 to 2 of, let's see, y to the 5th over 10 times 1/2 y to the 4th is y to the 9th over 20. Then you have y to the 3rd over 10 times 1/2 y to the negative 4th, that's going to be y over 20. And then y to the negative 3rd over 6 times 1/2 y to the 4th is y over 12. You could combine these together if you really wanted to, but I don't really see the point. And then finally, y to the negative 3rd over 6 times 1/2 y to the negative 4th is y to the negative 7th over 12. And then you can integrate each part and get y to the 10th over 200 plus y squared over 40 plus y squared over 24 plus, actually minus y to the negative 6 over 6 times 12 is 72. 1, 2, and then you can plug in the 2, subtract and plug in the 1, and some awful fraction. Okay. Surface area. You're welcome. Yeah, of course.
We do this definitely.
Probably, yeah. What is it?
It's from 0 to from 0 to 3 over the square root of x times e to the negative square root of x.
Oh, yeah.
I know it's a new stuff, but I found that.
Sure. So we've got the integral from 0 to 2 of 1 over
3.
3 over.
Yeah, 3 over square root of x. Times e to the, or and then
To the outside of it.
so outside of it.
Sure.
Times e to the square.
Cool. And we're at the stage in the game where any definite integral has the potential of being improper. And this one is. So the first thing here is to recognize that this integrand is undefined when x equals to 0. So we should firstly rewrite this as the limit as a approaches 0 from the right of the integral from a to 2 of 3 over root x e to the negative x. Although if I was being a little bit more diligent about things, I would probably just bring that 3 out in front. And then, since I see it's not just a straightforward, I know the answer, I'm going to do the indefinite integral off to the side. Because I don't really like having to carry all of that machinery with me if I'm trying to integrate something more complicated than just something straightforward. So for the integral of 1 over root x e to the negative root x, you have two good choices for you. You can either choose just root x or negative root x. I would probably choose the entire exponent. I would probably choose negative root x. So I'm going to pick my u equal to negative root x, which is negative x to the 1/2. My du is negative 1/2 x to the negative 1/2, which is negative 1 over 2 root x. So I don't really want the negative 1/2 part, so I'm going to say that negative 2 times du, oh, don't forget the dx there, sorry about that. Dx there. Negative 2 times du is equal to 1 over x times dx. So here's my dx over root x, which is equal to negative 2 du. And here's my e to the u. So it looks like I have the integral of negative 2 e to the u du, which is equal to negative 2 e to the u, which is equal to negative 2 e to the negative square root of x. And if we wanted to check, just to be sure, we could take the derivative of it. I don't think we need to check though. So then we go up here and we say, great. This is going to be equal to the limit as a approaches 0 from the right of 3 times the integral of 1 over root x e to the negative root x is what we just found. It's negative 2 e to the negative root x, evaluated from a to 2. Surprisingly picked 2 and not like 4. 4 seems like it would have been a much nicer choice, but I'm not the one making it up. Sorry, this is cool. And then we get the limit, say it goes to 0 from the right, we plug in our limits of integration. So we get, it's probably multiplied by 3, oh well. So we get 3 times negative 2 e to the negative square root of 2 minus negative 2 e to the negative square root of a. And then we let a go to 0. And in this case, that means you can just plug in 0 for a. Because the square root of 0 is 0 and e to the 0 is 1. So we end up getting 3 times negative 2 e to the negative square root of 2 plus 2 times e to the 0. Which you could leave as is, or you could simplify. If you factor out the 2, you can say it's going to be 6 times e to the 0 is 1 minus e to the negative root 2. That's probably how I would choose to write my final. Yeah, Rowan, it's a good question. Anyone on Zoom have anything they want to see? All right, well, I think I'm gonna call it a day because the board's not my friend. Yeah, I'm gonna call that number after class and hopefully get this fixed for Thursday. Thursday, the plan is to it's kind of a free-for-all review. I will certainly come with review questions of various topics, integration, like all the methods of integration we've talked about, stuff we've talked about recently. You should come with questions as well. I'll see if your instructors have posted any sort of final reviews, and you can kind of just do whatever you want to cover before your finals next week. What days are your finals for this class? Wednesday?
Parallax.
Parallax Tuesday? Okay. As far as availability, we'll have office hours starting on Friday. Friday's the first day of finals in drop-in. And then on Monday, Tuesday, Wednesday, we'll be in drop-in as well.
Okay.
I think from 10 to noon and 1 to 3, it'll be the Remir grant.
Is that?
In the library, yes, in the library. So not our usual office hours in various places across campus.
Thank you.
Thank you. Thanks for sticking with me.